Is it going? All right, so we left off last time with the idea of generalizing the two impulse maneuver we called Hohmann transfer to three ellipses, where the start orbit, the target orbit, and the transfer can be in general elliptical. So we're going to generalize two impulse maneuvers to the most general case, where without loss of generality, this is my start orbit, then my goal orbit is, for example, an ellipse which is bigger semi-major axis, and once again this is general. What we're going to do is general. So if this looks like the perigee and this is the apogee, it could be the other way around, and the same for the outside ellipse. We're going to find general solutions that work in all cases. I want to change color. I don't need to change color, to be honest. So now, if you go back to what we done last time we said the Hohmann transfer is the simple circle-to-circle maneuver, right? So in this case, it really doesn't matter if you're starting the first burn here and then you run half of the Hohmann transfer and then you burn here, or you do it here and then you go on the same type of ellipse just a little later. It doesn't really matter. The delta V's are going to be the same. You're going between the same circles of the same radius, and you're using the same type of transfer ellipse. The same major axis of this ellipse here or this one here are the same. So it doesn't really matter where you start. You're going to end up on the same big circle. Okay? Your phase, if you want, your location is going to be different, of course, but the delta V is the same. Now, the same does not work here. It does matter where you start. And do you see two different options? I know my drawing is probably not that great, but those are supposed to be two ellipses, not two potatoes. So what can I do? I am on this one. Let's start giving names to the different trajectories. Let's say that this is my starting trajectory and this is my goal trajectory, 1 and 2. So I am flying on 1, and this is my attracting planet, probably the Earth. So if I want to do a two-impulse maneuver, that will probably start at apogee and perigee. We'll get to maybe doing more complicated things, but let's look at these 2 points. I have two options here, right? Which is exactly starting from this point here and going on this transfer ellipse and stopping here. So first burn is here at perigee in this case, looking at this sketch, and then I guess that would be the apogee of the outer ellipse. So that is the option that I call 3. Right? But I could also start here and go on a transfer ellipse and then burn here, fix the velocity, and follow this path, which is 3 prime. They will probably give me different delta V's. Okay? So let's give a few names to points here. So this is A, this is A prime. Let's call this B. And this is B prime. The only reason why they are in this order is that the trajectory without the prime connects point A and B without the prime, of course, and A prime, B prime is they are connected by 3 prime. And let's call these distances, this is RA, okay? This will be, of course, RA prime. Etc. So this other one, I'm going to go up here, is RB prime. And finally, I have RB. Understandable enough? Yeah, I think so. Okay, so we want to find the different delta V's for option 3, A to B, or 3 prime, A prime to B prime. And I'm going to do it for a couple of points, and then I'll just give you the final expression, because it's really no different than what we have done last time. But let's say that we start at A, and we want to go on trajectory 3, and then fire at B. Okay, so what happens at A? So at this point, I hope it's clear that all we're doing here is connecting conics. You merge a conic to another one by fixing the velocity, by giving a delta v, right? So I am on trajectory 1 to begin with. So on that orbit, I have the following expression for the energy, minus mu over Ra plus Ra prime, right? This is my 2a on that ellipse. Agree? This ellipse, 1. Ra plus Ra prime. This is terrible, R. Okay? So that is equal to the velocity that my spacecraft has at point A if it remains on trajectory 1 squared over 2 minus mu, the distance from the focus, which is in this case Ra. So that's what happens if I am on 1. If I am on 3 now, the same expression is the following. So now I'm looking at this half ellipse here, that is the transfer ellipse, whose semi-major axis is Ra plus Rb, twice the semi-major axis. And this is going to be equal to my velocity at point A if I am on trajectory 3 squared over 2 minus mu over Ra. Agree? Yes?
So is there a different name for this? Like Hohmann transfer was 2 circular orbits.
This is, or you can call it a Hohmann transfer, generalized Hohmann transfer. It's a two impulse transfers. That's what we can call them. Yeah, I think you can call the Hohmann transfer. If we have time, we'll start looking at 3 impulse maneuvers. They're called bielliptic maneuvers. They're still called Hohmann, bielliptic Hohmann maneuvers. Yeah. Okay, so, well, the delta V is, of course, the difference of those. I'm going to ask you this question until you get used to it. Is the delta V going to be increasing my velocity or decreasing my velocity? Increasing, I'm going on a bigger trajectory, higher energy. So it's going to have an increase. And so at the point A, I'm just going to give it to you here. So you basically solve for this, for the 2 velocities, take your square roots, and subtract. Delta V in A is going to be equal to square root of 2 mu that multiplies the following. 1 over Ra minus 1 over Ra plus Rb minus another square root. 1 over Ra minus Ra plus Ra prime. Are there any questions?
Those are being multiplied?
Yeah, that's times this parenthesis. Yep. And then you have the same procedure applied to this point. Do you want me to do it? Basically rewrite the energy equations for this point?
Yes.
Yes. Okay. Are you sure? I'm going to speed up if you slow me down at some point. Okay, point B. What happens at point B? You tell me, though. I think you should be able to tell me. So we're traveling from 1. We have traveled from 1 to 3. Now we're flying on 3. We're coming into 2. So at point 3, what happens? I mean, on trajectory 3 at point B, what happens? You basically have to write this thing all over the place. Every time you do a maneuver, this is what you write. Right? It's just that the 2A becomes what it needs to become depending on the trajectory you're on. And the R is the position you're on, which will be B. And the velocity is what you need to find. Okay, so how does this translate at point B if you are on the transfer ellipse? Tell me. What is 2A?
Is it the same as the second part of it?
Yeah, it's the same trajectory, right? Ra plus Rb. This is what I want to find, the velocity of B on trajectory 3 squared over 2 minus, what is my R? Rb, okay? And then, so this is on 3. Now I want to find out the same for 2. Trajectory 2 minus mu over, what is the same major axis? Or twice the same major axis? It's my final goal, bigger ellipse. Yep. It's equal to velocity b on trajectory 2 squared over 2 minus mu over the same rb. So I don't think I need to write what the delta v is. If you want, I'll write it, but you know, yeah, let's finish this just for completeness. Then you can do the 3 prime. Nothing really changes. So as you solve for this velocity and then for this velocity and you subtract them, and what are you going to do there? Are you going to increase the velocity or decrease the velocity? Increase the velocity. The delta v you get, you know what, I'm going to put it down here so it doesn't look strange. Delta v in b is square root 2 mu. It's not that different from that one. I hear a lot of talking. It's not that it's distracting me, but if there is anything you want to ask, you should ask. Everything is clear? No? Yes? You don't know? Yes?
Above the expression you just wrote, that b, whatever, what's that?
B.
Thank you.
Yep. B on trajectory 2. When we get to interplanetary trajectories and what is called the idea of the approximation of patched conics, we'll do something similar. We'll connect hyperbolas to closed orbits. But that's the same idea. You connect at some point two different types of orbits and you fix the velocity. Yes, there was a question.
So on the mu over r component, it's rb for this example because that's where we're ending? Like,
Yeah.
Okay. So
Yeah,
if
yeah.
we were to analyze a different place, it would be different r.
So every time you compute a delta v, since we're doing impulsive maneuvers, you should expect these two guys to be the same because, as we said, we approximate that the engine is powerful enough and quick enough to give a burst that doesn't really change substantially the position. So every time you give a delta v, the position doesn't change. It's not true, but it's not going to change substantially, so we neglect that. So every time you compute at one point the energy equation, and then at the same point the energy equation, it is the same point, so this mu over r is the same. Then you solve for the velocities, subtract them, and find the delta v. Make sense? Okay. Now if you do, I'm going to show you an image here. If you do the same for A prime and B prime, so if you instead start here, the difference will be on that equation right here, this will be the same. This will be the velocity at point A prime on trajectory 1, and this is going to be mu over RA prime, etc., etc. So you just change, I guess, the RA into RA prime and RB into RB prime. You get very similar expressions for the delta V's, which I can give you. It's really not that different. But then, why am I bothering doing this? Because the goal is choosing between those two, right? If you have two options, which one do you think you need to pick? Bless you. Cheapest, smallest, smaller delta V, right? Why would you pick the other one? Unless it's faster and you have a time constraint. That would be a good reason. But in general, fuel wins over time. Okay, so this will be the delta V here to go from trajectory 1 on 3 prime, and then the delta V at B prime to end up on 2 again, just at the other side. It's very similar. Prime minus 1 over RB prime minus 1 over RA plus RA prime. Okay, fine. Now, establishing now which of the two is more convenient cannot really be done analytically, and there are some images on your book that are very useful. So, trajectory, I erased that one. But the trajectory tree was giving you a delta V in A plus a delta V in B that you have to compare to these two, the addition of these two, right? That's the cost you pay. Bless you. So if I can get this thing to turn on. Yeah. There are some interesting plots, contour plots, that show you the delta V's related to each other. Oh yeah, laptop, that's why. Here it is. Okay. So these should respect the same names for the positions that I gave you. So again, this is just an example where this is the perigee and apogee. It could be the other way around, and the same for the outside ellipse. The starting ellipse could be a circle. So this is the most generic you can think of. So let's look at these three contour plots. The lines here that you have, the numbers 1.1, 1.2, etc., they are the ratio between the delta V total that you pay on trajectory 3' over the delta V that you pay on trajectory 3. Okay? So how much the bottom trajectory costs you over how much the top trajectory costs you. So if this number is greater than 1, which one would you pick? So if delta V total on, what is it, 3' over delta V total on 3 is greater than 1, which one wins? 3, right? Okay. So if I go to this contour plot here, I see that all the numbers are basically above 1. So 3 is winning there. And what is happening, this is an example, but it's really, if it's valid in general, is that plot belongs to a case where RA prime is greater than RA. It's 3 times more in this case. But that means that this is the apogee. So you start at the apogee. In that case, it is better to do this one. Which one do you want to do? Are you starting at the apogee? I'm sorry, I'm correcting myself. RA prime is greater than RA, and that's fine. So this is the apogee, this is the perigee. Do I need to start at the apogee? I should have asked the question rather than making a false statement. Should I start at the apogee? No, because 3 wins, right? So this is the physical situation that that plot number, what is it, A, is showing me. This is where I start from. This is actually the apogee, and this is the perigee. But that plot is telling me that I should pick this one. So I start at perigee. Okay. Then I'm going to skip the middle one for a second. The other case, the opposite, where I swap the order of RA prime and RA is, now this is the perigee and this is the apogee, even though I don't have an image for that, but that would be the case. Which one wins? 3', right? Do we see that? The last plot. I'm skipping the middle one. I'm looking at C. So the ratio of this delta V is the same one. Now it's looks like it's always less than 1, right? So I pick this one. Yes?
Sorry, can you explain that again?
Yeah. From the beginning? Plot A?
There was like a lot of pointing.
Okay.
Sorry.
All right, so forget about these two, B and C. Let's look at A first. A is a bunch of options for RB and RB prime. See, RB and RB prime are changing. Everything is normalized by RA. So RA is, they decided to create these plots normalizing everything by the radius of the position A. But so this, on the x-axis you have variation of RB, on the y-axis RB prime, but it doesn't matter what they're doing. All these lines here that represent the ratio between how much you pay on trajectory 3' and how much you pay on 3, they all give you a number greater than 1. And that belongs to the case where RA prime is greater than RA. So it's exactly this sketch right here. So if I start from an ellipse where A prime is apogee and this is perigee, it doesn't matter what B or B prime do, because every relationship, every single time you try to do a maneuver to a bigger outside ellipse, you get in this ratio greater than 1, which means this is costing more, right? Make sense? Yes?
So, are you going to explain it? Because I don't want to interrupt.
I don't know. Depends.
So, the faster your velocity is, then you start at perigee, right?
In this case, it's convenient to start at perigee, because trajectory 3 is preferred in this case.
Wasn't that at the other one too? The higher velocity you had was at perigee?
Yeah, I was going to get to that, yeah. So, but let's first convince everybody that, so again, forget B and C, okay? That plot is, someone decided to plot a bunch of combinations for basically RB and RB prime, deciding that the initial trajectory is such that the distance between F and A prime is bigger than the distance between F and A. That's why on top of the plot you see RA prime divided by RA is 3. But this is valid for 5, 6. As long as this is apogee and this is perigee, that's something you're going to get. You're going to get that this ratio is always greater than 1. I mean, how do you do this? Well, you do it with those delta V's that I computed, and you change all those RA and RA primes. You change a bunch of values and you create a plot. That's what they've done for you here. Yes?
So you're basically saying that
The conclusion of that is the following. You start from this configuration, you better start from perigee and go on this trajectory, because if you do it from here, you're going to pay more. It's always more expensive in terms of delta V. That's for picture number A, letter A.
So will that be the case for all general?
Every time you start, so this is a 2-impulse maneuver, first of all. I haven't computed more than 2 impulses, right? A 2-impulse maneuver where my start orbit is an ellipse, and it doesn't matter what the outside is doing. So this could be the apogee or the perigee. It doesn't matter because it's always greater than 1. So if you're starting from an inner ellipse and you're trying to go to a bigger outside ellipse or circle, it doesn't matter, you want to start at perigee. Okay? That's the conclusion from the first plot.
Are the physical distances of the path and read prime the same?
No. They don't have to be. It depends. No, they don't have to be. No. Now the opposite situation, which is plot number C, is now, if you want I can sketch it, but it will be as ugly as this. That this is now not the apogee, it's the perigee, and this is the apogee, right? That's the last one, the third one. Look at the top. It's telling you that RA prime is smaller than RA. And that is, in that case, is 1/3. But again, it applies to every time that ratio is less than 1. Well, again, it doesn't matter what RB and RB prime are doing in that plane. The ratio between the delta V's is always less than 1, which makes me prefer, in this case, the 3' trajectory, right? But guess what? This is the case where this guy has become the perigee. So this is telling me the same thing. You start at perigee. So the conclusion of those two plots combined is that I do not care about what I want to obtain outside, if it's an ellipse, which one of the two is the apogee or perigee. If it's a circle, it doesn't matter. You start at perigee if your inner orbit is an ellipse. Make sense? Yeah, either way. You can start. You can start.
No,
Okay.
So then if the outer orbit was a circular orbit, you
Same.
still want to be in perigee if they
You fire a perigee, yep. And then you fix the, when you reach the circular orbit, you correct to reach a circular velocity. That's all, yeah.
Does this have something to do with the fact that the velocity is greatest at perigee?
Well, yeah, you need to accelerate less. Yep, that makes sense. You want to go to a faster trajectory. You're already flying the fastest you can on 1. Yep, you push less, yes.
So this still applies even if the orbit you're trying to get to, you're going to land in the perigee?
Oh yeah, it doesn't matter. Doesn't matter, yeah. If this is perigee or apogee, it doesn't matter. Again, if you look at those plots, RB and RB prime, they can be all over the place. It doesn't affect you. Now the middle one, yes.
Do these plots still hold true if you're trying to go to a smaller orbit?
Yeah, I'm gonna address that in a second. So this is an example where I'm going from small to big. But as we said last time, the magnitudes of the delta V's, the actual numbers that you get, except the vectors, right, in which direction you fire, the number, the amount of fuel you burn, it's the same. If you go from a small circle to a big circle or vice versa, the same circles, the amount of fuel you burn is the same. You just invert the direction of the burns, right? So we're going to revert this in a second once I'm done discussing the middle one, which is, now what if my inside object, ellipse collapses to a circle, right? What do I see there? Now this makes a difference where I end up going. Okay, this is, the line 1 means that they cost the same, right? Doesn't matter if I go 3 prime or 3, they cost the same. The ratio of the delta V is the same, but that line is also the line where RB and RB prime are the same. So I'm going to a circle, that's the Hohmann transfer pretty much, right? That middle line. But what about below the line? Below the line, RB is bigger than RB prime, right? You see that? This is the line of RB equal to RB prime, except it's normalized, but that's the same. So in this part of the plane, RB is greater than RB prime, and which trajectory wins? That's what I have, right? So I win with the bottom one, the 3. And I'm saying that RB is greater than RB prime. So this is the apogee. I am going to the apogee. Again, I'm starting from a circle. So now that I'm starting from a circle, I can't really say start at apogee or perigee, it's a circle. Start so that you end up at apogee. That's what that part of the plane is telling me. If I go up instead, where RB prime is bigger than RB, so on top of this line 1, the situation is inverted, where this is less than 1, and so I want to be on this one. But RB prime is greater than RB. It's the apogee again. No? Conclusion is, do whatever you want. If you start from a circle, you want to end up at apogee of the outside ellipse. Doesn't make sense? I can keep explaining this. This is important. You need to be able to read, navigate these plots. Yes?
Why, theoretically, wouldn't it be more cost effective to go to perigee, which would be closer? I mean, I understand mathematically why it is, but...
Well, the reason is it's closer, but when you maneuver, when you have to fix the velocity at perigee, that's the highest you encounter, so you probably have to give a bigger delta V. But again, in some cases you can intuitively explain what's going on, but look at these relationships behind the screen. They're all non-linear. Square roots 1 over r's is not that straightforward. That's why they create these plots, these contour plots, so that you have them once and for all for a bunch of combinations of radiuses, and you can tell which one to pick. It's like having a lookup table, pretty much. That's how you should look at these. They are a manual for you. I want to go from this trajectory to this one. Which one do I pick? Well, let's look. Stick in the ratios that you have for the radiuses and decide which one you want to use. Yes?
What are the tolerances for like the moment in which they have to do these burns? Like if they're off by like 3 seconds or so?
Well, seconds. So let's put it this way. It depends on your orbit. If you are in low Earth orbit, the International Space Station goes at more than 7 kilometers a second. If 2 seconds is what, 21 kilometers? Is that a lot? It depends if you. It really depends on what you're doing. So if this is, say that this is a spacecraft in low Earth orbit, and it's doing this maneuver to reach another spacecraft that is in this bigger orbit here, right? And you timed everything correctly so that this other second spacecraft is flying on its trajectory, and it's going to be here exactly at the right time if you start here. Well, if you start a little later, first you're going to probably end up somewhere else, and the timing may be off. It really depends on the application. If it's rendezvous, you need to be very precise. If it's just a course correction to just go to a bigger orbit where you don't need to encounter anything else, then you probably can wait a little bit. Yeah?
So when we launch a spacecraft to the ISS now, is the trajectory, like, does it have to, when it launches, does it go into a smaller orbit and then go and meets up with the ISS, or does it just go straight for the ISS?
I don't believe there are transfer orbits. I think they just go up to the right altitude. I may be mistaken, and it may depend on the rocket that brings you up, but I don't think there are transfer orbits. So I think the windows are calculated so that you go up with 1. Well, you wait several orbits in going up, but there's no impulsive maneuvers, I think, done this way. Yeah.
With respect to what you just said about being a few seconds late and whatnot, what about decelerating with respect to if they're on the same level, so that one catches up to the other?
Could you re-ask the question? I'm sorry, I didn't.
Say you did miss it by a few seconds.
Yes.
And you meet it behind the ISS.
Oh yeah.
What if you just accelerate within the orbit?
You can do. I mean, so first of all, we're still doing impulsive maneuvers, right? So until we're done with impulsive maneuvers, we don't have the luxury of saying I'm going to turn on a thruster for, I don't know, 3 minutes and reach that object, right? We don't do that. But one thing that we're going to do in the next, well, at least next time, is there are what are called phasing maneuvers, where if you are on the same orbit, say it's circular orbit, right? This is your focus, your attracting planet, and you are spacecraft 1. Actually, you know what? Let's call this, even if it doesn't fly anymore. This is the shuttle, right? And this is the International Space Station, and you're off. You are on the same orbit, so if you don't do anything, these guys just keep chasing each other. But you want to reach it. Well, what I think I mentioned this last time. You can do basically an impulsive maneuver that leads you into a smaller orbit that is a little faster, so that with this period here, you cover this time that the ISS takes to reach the same location, and then here you correct again the velocity and you are at the same location. So if you are behind or ahead, you do usually a rephase. If you want to do it impulsively, like we're doing for now, not continuous thrusters, you do it with the rephasing maneuver. You play with the periods of the orbits, because a bigger orbit has a longer period, a smaller orbit has a smaller period. So you play with those so that you synchronize the locations. And we'll see them. Do you want me to re-go through these again? Okay, I think it's worth it. So the way you want to look at these plots are the following. This plot shows you the case where your starting orbit is such that what I called A prime is the apogee and A is the perigee. This is the opposite case. It's a circle, okay? So we start from this one. The 3 plots are set by that relationship between RA prime and RA. So they're basically telling you what is the shape of your starting orbit, right? Which one is the perigee and which one is the apogee. In the 2 extreme cases, and in this case they don't exist, it's a circle. Fine. Then they have changed here a bunch of values for RB and RB prime and computed the delta V's with the formulas I gave you for trajectory 3 and trajectory 3 prime, right? So we look at this one and we see that what they're plotting is the ratio between, it's not here anymore, it's gone, delta V total on 3 prime over delta V total on 3. That's what you have on those lines. So in other words, if I pick an RB over RA of 6 and I pick an RB prime over RA of 4, I go up here and there should be a line here, one of these plots, that tells me what is the delta V, right? That's what they've done. They have covered a bunch of combinations of those radiuses. But it doesn't matter what I do with RB and RB prime, I always see something greater than 1, which means that this is greater than 1, which means that I want to do this. I want to be on orbit 3. So that's the case, RA prime greater than RA. Orbit 3 tells me that I start at perigee. Are we fine with that? Yes?
So you're going from an ellipse to another ellipse, you always want to start after.
Yep. If you start from the ellipse, you always want to start at perigee, pretty much. Because if I look at that plot, where now RA prime is the perigee, and again RB and RB prime can do whatever they want, the ratio here is at the most going to be 1, which is meaning that they are equivalent. And so this situation is inverted here. So that's the case where this is closer than this to the focus, and they're telling me that I need to pick this trajectory, so I'm starting again from the perigee. So you combine A with C, they're telling you if you start from an ellipse, inner ellipse, just start at perigee. It doesn't matter what your target is. It can be a circle, it can be an ellipse with the perigee and apogee in any order. You want to start here. While the middle one is I start from a circle, and that makes a difference being on RB greater than RB prime or not. So this is the Hohmann transfer, right? I go from a circle to another circle. When RB is greater than RB prime, which is the semi-plane below this line 1, I'm down here, this ratio is greater than 1, okay? If that's greater than 1, I pick 3, the smaller. And so that is the case where RB is greater than RB prime. So I go at apogee, because I pick 3. If I am above that line with the 1, RB prime is greater than RB. So this is the apogee. But guess what? This relationship goes the other way. So I'm going to pick the trajectory that goes to the apogee, 3 prime. It's just if then else, if then else. That's all I'm doing here.
So going from an inner to an outer orbit, you want to start at the perigee and the apogee. Is it the same way going from outer to inner orbit? You want to start at the apogee and at the perigee?
Yeah. So since all that we're doing is impulsive maneuvers and everything can be inverted, so imagine now that you start from a bigger whatever, circle or ellipse, and you want to target an inner ellipse, exactly what he said. You do what it takes so that you end up at perigee. When I go from inside to outside, I start at perigee. When I go from outside to inside, as long as the inside is an ellipse, I stop at perigee. Make sense? So if instead of flying things this way, right, on this same sketch, I'm imagining that this orbit is run this way by the spacecraft, and then I transfer here, or I transfer here, and then I end up on the bigger one going in the same direction, which is counterclockwise. Well, imagine that you're doing the opposite now. Flying this way, now the transfer is this way, and you end up on the smaller ellipse like this. Well, the same reasoning goes for this situation. You want to start your maneuver such that you can stop at the point which is the perigee of the inner ellipse. Do you agree? Okay. So that basically covers case A and C. Case B, what do you want to tell me for that? If I was starting from a circle, inner circle, and I was going to a bigger ellipse, I said, I need to make sure that I end up at the apogee. Now invert the problem. You start from the bigger ellipse, you want to go to a circle. What do? You start at the apogee. So you end and start at the same locations, pretty much. You just invert in the direction, if you want. But that's really what happens with impulsive maneuvers. They're just corrections in velocities. They don't change the magnitude if you're going from A to B or from B to A. You look confused. Are you confused? A little bit? We can go back on this if you want. I wanted to give you an example here. So what is the point of doing all this? Why do you even care about this? Because if I give you, or someone gives you, two trajectories that are closed trajectories, this is the most general case because the inside can be, if we're talking about closed trajectories, can be a circle or an ellipse, right? And the same for the outside. And if you're doing a two-impulse maneuver, that's covering everything. So if someone is giving you an inner ellipse, say that you're going to a bigger orbit, well, that someone is giving you RA, RA prime, RB, and RB prime. Look at those numbers, actually compute those ratios, look where you are in these planes. First thing you do is RA prime over RA, so you know if you're here, here, or here. Once you've chosen what plane you're looking at, then make your conclusions. When you need to trust, if it's perigee or not. Okay. I'm assuming I'll see a lot of people about this at office hours, right? No? Let's look at this. Well, I started. I don't know if I can finish it, probably. Let's look at this problem here. That has to do also with the question of timing when you do these maneuvers. This is also another problem from your book. Okay. So, this was supposed to be a circle. Let's see if I can do something better. More or less. Does it look like a circle? No. But it is a circle, believe me. Just imagine a circle, okay? Maybe it's better. Okay, so this is a circular trajectory of the ISS. Why not? ISS is here. And I don't have the text with me, but what they're telling you basically is that there is a spacecraft coming from who knows where on a hyperbolic path. Okay? They're telling you where the perigee of the hyperbolic trajectory is, which is some r of the Earth plus 5,000 kilometers. So that's the height of the perigee. They're telling you that this velocity right here, let's call this point A, v at A is 10 kilometers per second. So you're coming in this way, okay? And the question is, I'm going to go on a transfer ellipse here. They're telling you compute this transfer ellipse, first of all, so that you end up on the same circular orbit of the ISS with two impulses, one here and one there, of course. There's no other choice. And then I think there is a question asking, what is this angle? Let's call this point B. So that's the point A where you do the first impulse, and this is point B, do the second. What is this angle, phi, from point called ISS point C, C to B, so that this spacecraft coming in from far away is going to match the ISS here? So at what, basically, it's almost like asking, at what time do I start this maneuver here? At what time do I need to be here so that I do a two-impulse maneuver and I'm going to find that the ISS is there? So before I even compute the delta V's, which is really not a big deal because we do the same that we've done last time, there's one radius missing. What is it, 500? It's a little high for the ISS, but that's fine. So this is trajectory 1, and call this 2, and call the transfer 3. It's half an ellipse. Forget about the delta V's. How would you approach the question of what is this angle? Again, the idea is that I reach this point, and the time, basically, the time it takes me to get here is the time it takes the ISS to get here, so that we meet, right? Yes?
So like the mean anomaly of the ISS orbit, how long it takes to go all the way around? Or you can calculate that. You can find the period, and then you can find
the period. It's probably, okay.
ISS.
So there are, how many periods do we need to talk about here? Yeah, 2, right? Which ones?
ISS and
ISS?
Do we know where the ISS is?
No, I don't know. So the question is that I don't know. So this is unknown. I don't know this. I know the radius of this orbit, but I don't know where the ISS should be when I reach this point with respect to this direction here. So we're getting there. You need to compute periods here. Which periods? By the way, this is the expression for period. Okay. So that's valid for a circle, for an ellipse, it doesn't matter. Okay? So how long is it going to take me to run this half ellipse here? T of 3 is 2 pi over square root of mu. What goes in here? That's the period of the transfer ellipse, right? It's 2 RE plus, well, in this case it's 5,500, right? Divided by 2, because that's 2a. Yeah. You see that? If I fire here and I put myself in this ellipse here, but then I don't do anything at B, I keep going on this ellipse, and that's its period. Right? Okay. That's one piece of information. I actually have it. It's about 5,676.8 seconds. What about T of 2? Hold on a minute. I'm swapping them. Wrong number. Okay. Yeah. Well, the same story, right? Except this is the A in the case of the ISS is just RE plus 500, so you do the same. 5, 6, 7, 6, 8. These are seconds. These are seconds. Well, I'm sorry, what was the question?
A for the international space station would be
it's RE plus 500.
it's just radius.
Yeah, it's A. A, it's the same image axis. So it's, in the case of the circle, it's diameter divided by 2, so it's the radius, yeah. Okay. So what do you want to do? I think I swapped them again. I think I had it right before. What do you think? So let me ask you this question. Do you think which one of the two periods should be bigger, the circle or the ellipse? Which one? The ellipse is bigger? The circle should be bigger? Why?
Because if you're rendezvousing at B with the space station, then half, or the trajectory 3 will take the full time, but the space station has the head start from B, so it should take longer.
Well, actually, from my calculation, what I have is this is definitely half an orbital period, right? Okay. And so this should take the same time, right? I'm not saying it's wrong, I'm just asking if that makes sense to you. So T3 is the ellipse. The period of the ellipse is bigger than the period of the circle. We're fine with that? We're fine. Same major axis of the ellipse is bigger than the same major axis of the circle, right? I'm fine with that. I'm just asking you. Yes?
Don't we have to figure out the angle of the...
Yeah, we need to figure out that. But we need to play with the periods, because what happens, what I'm going to impose is that in half an orbital period, basically in T3 over 2, the ISS is going to run this angle that I don't know, right? What is that angle? Let's put it this way. The angular velocity of the ISS on its orbit is given by what? 2 pi over T2, right? Is that right? Agree? Disagree? I don't want to do it. I have the numbers here. I'm just asking you. By the way, this delta V I will get to finish this. Tells me that I'm going to use 85% of the mass of the spacecraft. Yeah. Do you agree with that? If T2 is the orbital period of the circle, that is the angular velocity, right? Okay, what do I do with that information? Good. I'm sorry, I can't hear from here. Yeah. Is that a suggestion? Period 2 times omega. Okay. It's going to give me 2 pi. No? So it should be not that tricky, right? But okay. I said that I'm going to definitely run the orbit 3, only half of it, right? So I think the angle between C and B should be the angle that this angular velocity is going to allow me to cover in that amount of time. So I think this is what it is. No? $275.2 degrees. Does it make sense? The question is, what is this angle here? So basically, where is the ISS? So that if I start transferring from this hyperbolic orbit into the circle eventually, I reach it right there at point B. Well, this is trajectory 3, its period is whatever it is. I only run half of it. In that same amount of time, I have to cover this angle, right? I know how fast I'm going on that circle. We need to stop. Try to finish this. We'll pick it up next time.